Okay, so this is a question number 6. I can't remember what year it's from. It's either from 2003 or 2006. I don't remember. And it was part B, which is the makeup exam. So it says, in September of 1990, each student in a random sample of 200 bio majors at a large university was asked how many lab classes he or she was enrolled in. The sample results are shown below. So then we have this table that says you could take between 0 and 5 lab classes, and it tells how many students fit in each of those categories. Off to the right, it shows us the sample mean of 1.83, standard deviation of 1.29. Next part, it says to determine whether the distribution has changed over the past 10 years. A similar survey was conducted in September 2000 by selecting a random sample of 200 bio majors. Results from 2000 are shown below. Same information, you can take 0 to 5 lab classes, tells you how many students, tells you the sample mean, sample standard deviation. Okay, so A, do the data provide evidence that the mean number of lab classes taken by bio majors in September 2000 was different from the mean number of lab classes taken in 1990? Perform an appropriate statistical test using alpha equals 0.1 to answer this question. Okay, so do the data provide evidence that the mean number of classes is different? What type of test is that? They're looking at
match pairs for me.
No. They're looking at the mean number of classes taken in 1990, the mean number in 2000, 2 sample tests for difference in population mean. Yeah, I don't actually want to carry out the entire test. I just want to do the important parts of it.
Is there a significance level of 0.1 just because it's a homogeneity?
No, that's just what they chose. Okay, so I'm not going to define variables. I'm just going to jump right into the null and the alternative. So our null would be that mu1 minus mu2 equals 0. So I'm assuming that there's no difference in the mean number of classes from 1990 to 2000. Our alternative is that mu1 minus mu2 does not equal 0. So there is a difference. Either people are taking more lab classes on average or less. Okay, assumptions. What's the first assumption?
Random sample.
Random sample. Second assumption.
Approximately normal sampling distribution.
Before that. Independent. So remember the first two are random and independent, but I told you the AP test doesn't really like that wording. So what does that mean? Randomized treatments or random assignment. So are there independent random samples, which means that the treatments were randomized? In this case, no, not really. Do you randomly determine how many lab classes you're in? Like, did I go around and say, you're taking 2, and you're taking 3, and you're taking 1, and you're taking none?
We're not sure.
Do you think it's reasonable to think that they were randomized?
No.
Probably not, but anyway, just assume it to be true. And then the third assumption, or second really, is approximately normal sampling distribution. That one is true. Why are both sampling distributions approximately normal?
200.
N is greater than 30, thank you. We have 2 sample sizes of 200, so the central limit theorem applies. Yes?
What did you say we should respond for assumption number 1? Pursuit of caution?
Sure.
What was the second one?
Normal.
Yeah.
Okay, so then we're just going to jump right into the actual calculation. We're going to use T and not Z because we don't have the population standard deviation. So the formula is x1 bar minus x2 bar minus mu1 minus mu2 all over standard deviation squared over n1 plus the variance over n2. I'm going to do 1990, subtract 2000. So this is 1.83 minus 1.93 minus 0. Remember that this comes from the null, that's why I put it in 0. Okay, right now, can you calculate this t value, please? I'm very unsure of my answer, so you all need to calculate this also.
-0.75.
Taylor, did I mess something up?
Why is n tiny?
Oh, because it's not. Should be 200, right?
Yeah.
Okay, sorry. That's why it didn't look so right. Okay. Okay, Matt, what did you say it was?
-0.752.
Negative 0.752. Okay, and then it's a two-tailed test. So you're going to find the probability of t being less than or equal to that negative 0.752. And you're going to multiply it by 2. Matt, can you do that, please?
0.453.
0.453.
Did you multiply by 2?
Yes.
Okay, I'm sorry, Matt, what did you say it was?
0.453.
Okay, so in this case, we're going to say 0.453 is greater than our alpha of 0.1. So we are going to fail to reject the null. What does that mean if I fail to reject the null?
There's insufficient evidence supporting the alternative hypothesis.
So we don't have sufficient evidence to believe that the mean number of lab classes has changed. Okay, so this was review. Yeah, you guys remember this? Okay, here's where it all changes. Turn to part B. Okay, so part B says, does the test in A address the question of whether the distribution of the number of lab classes was different in 2000 than it was in 1990? If so, explain your reasoning. If not, carry out an appropriate statistical test. Okay, so do you get the difference in the question between A and B?
Yes.
A is asking, has the average changed? B is asking, has the distribution changed? So for example, if you look at the data set, the number of students taking 0 lab classes in 1990 was 28. That's 14% of students. So in 1990, 14% of students took no lab classes. I want to know, is it true that in 2000, 14% of students took no lab classes? If 31% of students took 1 lab class in 1990, is it true that in 2000, only 31% took 1 class? So it's looking at each individual category and saying, did those proportions stay the same 10 years later? Does that make sense, the difference?
So isn't that just like a chi-square goodness of fit test? Or where you do like the ratios and see like, is it different?
Kind of. With a chi-square goodness of fit test, you're given like a true distribution.
Oh,
We don't have a true distribution, we have 2 samples.
right.
We don't have a population. But do we understand now the difference in the 2 questions?
Yes.
Yes or no? Okay, so we understand that the test we did in A does not answer what we did in B. So we're going to have to carry out another hypothesis test. This is where that new test comes in. It's called a chi-square test for homogeneity. You might want to write this down. A chi-square test for homogeneity, you're going to see in 2 different cases. The first case is you're comparing 2 distributions for 2 years, like you are here. So here we looked at number of lab classes from 1990 to 2000. Second way that you're going to see it is it's going to be 2 distributions compared between 2 groups of people. So maybe I'm looking at the distribution of grades for females and males in AP statistics. And I want to know if girls have 20% A's, is that the same that 20% of boys scored or have an A? So you're comparing 2 groups of people.
What was the first case?
2 years. Second case is 2 groups of people. Okay. So, chi-square test for homogeneity is carried out exactly the same way as a chi-square test for independence. All that changes is how you write the null and the alternative and the name. That's it. So we're going to carry out part of it, we're not going to do all of it. Okay. So the null in this case. Basically the way this test works is you assume that one distribution are the true values. So I'm taking 1990 as my true values and comparing it to 2000. So my null is going to be that the distribution of the number of lab classes in 2000 is the same as in 1990. So I'm going to assume that they're the same, and I'm going to look for evidence to the contrary. So our alternative is going to be the distribution of the number of lab classes in 1990, in 2000 is different than in 1990. What's the first assumption? Random sample. Yeah, it says we have a random sample. What's the second assumption? Huh?
Independent.
No? The expected values are at least 5. Expected values are at least 5. Okay, so for a chi-square test for independence, the way you calculate those expected values is row total times column total divided by grand total. You guys remember that? Okay, so the way it works here is the same way, except you're given two different tables. So the first thing that you have to do is put them into one. So I'm comparing 1990 to 2000, and then you could take 0 through 5 lab classes. Okay, so you would have to find the column totals, you would have to find all those grand totals. You already know that your grand total is 400 because it's two samples of size 200. Yeah, so I guess you already know this is 200 and this is 200. Can I assume that you guys can calculate those expected values on your own? Okay, so right now put this table in matrix A. And then carry out the chi-square test. I believe you should get a chi-square value of 13.82. Somebody verify that? Yeah. Okay. Chi-square is always upper-tailed, so you then look at the probability of chi-squared being greater than or equal to 13.82, and that's approximately 0.017. Thank you. Hey, do you guys remember how to do this in the calculator? Okay, did we get everything in matrix A? Okay, so then if you go to stat and you go to the right to tests, it's chi-square test, which is in like A, B, C, like the alphabetical part. It's not the GOF test, it's not the goodness of fit, it's just chi-square test. Okay, we good to this point? Okay, so we reject the null. That means that the distribution of the number of lab classes has changed between 1990 and 2000. You have to remember that you compare that p-value to alpha. So we're going to say 0.017 is less than 0.1, so we reject the null. So I'm going to say I reject the null and instead believe that the number of lab classes has changed, or I guess the distribution of the number of lab classes has changed from 1990 to 2000. Okay, does this tell us how the distribution has changed? So if I look at the distribution, it looks like the percentage of students taking 2 lab classes has remained pretty much the same. Those taking 5 lab classes, it looks like that has pretty much remained the same. It looks like those taking 3, those taking 4, that's a pretty big difference, but we don't know for sure. Now, the other way that you could have answered this question is to compare each number of lab classes. So you could have done a hypothesis test for the proportion of students taking 0 lab classes. Then you could have done a hypothesis test for the proportion of students taking 1. And then for the proportion of students taking 2. So it would have been 6 hypothesis tests altogether. Besides the fact that that's not very time efficient, why else do we not answer the question that way? Alec?
Doesn't that still only show that there is a change just within each category? It doesn't show to what degree.
But wouldn't it give us more information than we have now? Because we would know where those changes occur, even if we don't know how big they are.
Yes, it still doesn't show how big. I thought that's
Okay, so I'm going to do 6 confidence intervals instead. Why wouldn't they do that? Jenny? Yeah, very good. Every time you do an additional hypothesis test, your error compounds itself. So you have an error here for doing 1 hypothesis test. When you do 6, it's even a bigger error than you started with. So our error right now is 0.1 because that's what our alpha is. But if we did 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, it just compounds on itself. So we don't want to keep building up the error, which is why we only do 1 hypothesis test.
How are we to know that the information that we would have received from doing 6 of those would be less valuable than the amount of the error would increase?
It's not that it's less valuable, the error compounds though very quickly. So the alpha for doing 6 of them, if I had to guess, would probably be about 0.5, which is pretty big, like a 50% error.
Don't just add them.
No,
So is there a formula for error compiling?
not that we have, no. Okay, so I know that we just did kind of the bare bones of this test, but do you guys see A, when this test would be used, and B, how to carry it out? Yes? No? Like 2 of you nod your heads, the rest of you just stare at me. Okay,
When we compare
Now-
the two.
my note to you is the reason that I've left this test until now is because it's only showed up in the AP test once since 1997, and it was on Form B. So the likelihood that you see it on this year's test is very, 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 very small. So if you think that you are using a chi-square test for homogeneity, please be absolutely positive that it's the correct test before you choose it. Got it? Be very, very certain. Katie?
Are there any tests or confidence intervals that are extremely common that they put on the AP test? Like, is there one